Dr. Channah is an associate professor at the University of Arizona, the Department of Soil, Water, and Environmental Science, and also maintains a joint appointment as a water quality specialist at University of Arizona Cooperative Extension. She manages several projects related to water quality and the creation of food safety tools for the industry. Have to tell you, we tasked Channah with bringing us home here. So she will be the last formal presenter. We lined her up specifically behind John and Kevin as a moving it from what EPA had on the research to a farm level. So she will spend 30 minutes making it all make sense.
I don't know if I can make it all make sense, but I'll try my best. You may or may not like me after this presentation. We'll see how it goes. All right, so I'll be fast and furious because we are quick on time. No? Okay, I'm taking my time. All right, so obviously we understand that microbial control is important for water, and that's largely due to the fact that microbes are acute health risks, right? So that is a more immediate need for some sort of reaction. And so I deal a lot with water reclamation facilities, drinking water facilities, and moving into this ag arena and trying to look at the things that we're doing in the water arena as far as protection of public health and how that might or may translate to what's going on in agriculture. And so I stole this slide from Brian Pexon. He's an engineer for Trestle Technologies. And when we look at general monitoring strategies, we often think about, is this more of an acute threat or is this more of a chronic threat? And the more acute the threat, the more continuous and the more rapid that we need to be monitoring these systems. And so again, we've talked a lot about frequency. We've talked a lot about monitoring and what makes sense for these systems and timing. And I think it's important to pay attention to this. One of the reasons you want to monitor some of these things more rapidly is because it gives you the opportunity to respond to something that might be off spec or out of compliance. And so again, we've heard that theme over and over again this week or the past couple days related to timing and when do you make a decision and when is the right time to make a decision. And so again, I like to put this one up because we talk about these numbers all the time, the 126 and the 410, but I don't think that we spend enough time wrapping our heads around what that means, right? And so this is a normal distribution of water quality samples, say, collected from any surface water or whatever water we might be looking at. And those goals of 126, that geometric mean would sit here, so the central tendency of the water, and that 410 would sit here, that statistical threshold value. And basically what that means is that 90% of the vast majority of those samples are below that 410 value, right? So that's a good image and something to think about as we talk about sampling going forward. And so Betsy and the team kind of asked me to talk about the potential mitigation strategies, and we've heard bits and pieces of those. And I'll just say I'm not advocating for one mitigation strategy over another, but just presenting various options that we know growers are doing now or considering or talking about as they're thinking about how they can meet the recommendations in the rule. And so obviously, if you're meeting those values, you're going to maintain normal operations. And then if you're not meeting a value, you're going to apply some mitigation strategy. And here are the 4 mitigation strategies. Again, I'll breeze through this. So looking at that time interval between irrigation and harvest, looking at the interval between irrigation and end of storage, you're treating that water or you're discontinuing use. And so there's a couple little bullets that I want you guys to pay attention to. So we've heard about the 0.5 log reduction per day, and I'll talk about that in a little bit. This one about irrigation and end of storage, the kicker here is what kind of data are you collecting, right? And what is FDA going to look at and approve and be okay with? There's a lot of ambiguity in that discussion right now, and so definitely there needs to be clarity there. Treatment of the water and some of the things that we heard yesterday that Trevor brought up about what are approved sanitizers and what does the EPA label say and how is that different than what's currently being done in practice and what kind of allowances can FDA discuss and allow. Because right now the way the language is it's very strict and it's very stringent and it might not make sense for the way that some of these adequate sanitizers might be used. All right. So some of the recent research objectives, so folks like myself, Trevor's group, Atwell's group, Dr. Gerba, and a lot of the folks that are in the room have been investigating irrigation water quality for over 20 years. So this is not a new research area. There's a ton of data out there. We would implore FDA to reach out to some broader groups and let us shovel our data at you, right? And so help you with some of these assessments, and so that we can build up that database and a better understanding. Likewise, irrigation districts in the West and growers in the West have been monitoring data as well, and so they understand their water sources potentially better than some other sectors that might not have had data yet and not had to think about their water yet. So what can we learn from those situations? So we've talked about risk-based approaches for water sampling. We've talked about some of the environmental impacts on microbial survival. And then lastly, I'll touch on some water treatment options available by industry. And so lots of evidence past this research shows us that we should pay attention to water as a potential vector for some of these pathogens. And talking about sanitary surveys, we talk about potential where these things might be coming from. So is it an illegal discharge? Is it a leaking septic system? Is it human recreation upstream of what might be our irrigation activity? Or is it wild or domestic animals? So we know that there's E. coli there. We're trying to determine where it potentially came from, and we're using a variety of tools to figure that out. Is it source tracking methods that we just heard about? Is it walking your watershed and doing a sanitary survey and using your knowledge of your area? And so some work that we've done that was funded by the Center for Produce Safety tried to evaluate some of these other environmental factors or irrigation water factors or other factors to help us make educated decisions about our water and potentially lead to a better understanding if there's a high risk for E. coli contamination or a lower risk. And so I'll walk through some of these. So things that we have to think about: temperature, salinity, pH, turbidity, any kind of organic matter. That's all going to play a role in the ability for that E. coli and other pathogens to survive or thrive in that system, or if we're going to see more rapid die-off. These are important factors. We've talked about this a little bit, touching on what is going on locationally. So are you on a main? Are you on a lateral? Are you looking at a pond? Are you in a reservoir? They all have different risk factors, and they all have different likelihoods of having higher or lower contamination. Other things about land use, we're looking at if there's bridges or roads, are there land slope issues, you have the potential for have runoff in a system. Those are all, again, things that you're kind of tallying up to identify, am I at a high risk or a lower risk situation? And the last thing, and this really plays into a role on die-off when we're talking about environmental factors. So you're talking about the variation in the growing area, and I just put this one up just as, you know, it's a vast valley. We have growing occurring in many different areas, and I'm not going to assume that the humidity and the temperature is exactly over here in Yuma Valley as it is in Mohawk Valley, right? And so it's different. There's site-specific locational conditions that play a role in the ability for those pathogens to survive and thrive. So some of this historical data that we kind of pulled together from multiple different regions, and so this is looking at Arizona, California, Nevada, and Oregon. We found relationships between some of those environmental and physical factors and the likelihood that we were finding E. coli in those systems. And so one of the things we want to say is, so can we look at those as predictors for E. coli? Can we use that available information when we can't go out and sample continuously? I don't know who's banging on a door. But more importantly, what we found in some situations is that there are some additional factors that we can't necessarily monitor for, but it's more likely who are we talking to, who are we communicating with? So in this case, the irrigation district, right? So they're doing canal maintenance during certain times of the year, getting them to talk to the growers in their area and say, hey, don't irrigate for 24 hours because we're doing some maintenance. And so we went out and we validated and tested samples over a period of time and saw the E. coli come up, and then we saw it drop, and it went away, and it was fine. And so, again, really simple corrective action, having a recommendation that you're communicating with your water provider and talking about things that might be going on. And so, again, that open line of communication we've heard over and over again the past couple days. And so again, just to reiterate some of those main influential factors that we found on bacterial loading, precipitation, we've heard that. We've talked about temperature. One of the big things that we saw was electrical conductivity or salinity. And so could this potentially be used as an alternative surrogate for monitoring that might lead us to think about how we're monitoring for E. coli in the future? And obviously sediment. Bacteria like to be co-transported with sediment at certain times and in certain circumstances. All right, so this is Kurt Nolte. Kurt Nolte now works for FDA, used to be at the Yuma Agricultural Center. This is how you find him all the time with his cell phone, talking to a grower. He's got a knife up in his hand, right? So he's been in the field. So how can we use all this information to inform industry? Because that's why we're here, right? Like, we can talk about all this amazing, latest, greatest science, but unless we're going to actually put it into practice, it's kind of meaningless, I think. So how can we do that? So again, we talked about risk assessment, and I brought up risk assessment yesterday and what is the acceptable risk. We heard Solar talk about potential risk assessments that he's been doing in the water scenario. And so this is what a potential event tree scenario would look like. So you know the number of E. coli in the irrigation water. You know the number that's transferred to the crop, potentially from past research studies. You can talk about survival on the crop pre-harvest, survival post-harvest, and then potentially the number that's ingested, and you can predict the probability of illness. Now, well, I will say that there's a lot of assumptions that are built into most risk assessment models, and it's only as good as the data that you're feeding into it. And so I'm going to walk through some of the data that we did in a little bit, doing this specifically with Dr. Gerba, looking at historical water quality data and looking at transfer data for different irrigation types. But really what we want to do is take a step back, right? We want to look at what are those things that we can look at and evaluate within our watershed that are going to allow us to predict that number of E. coli in irrigation water, or predict a high-risk scenario, or predict a lower-risk scenario. That's going to be the implementable tool that growers can use to make decisions about their water sources. All right, and so these are just some examples of pictures and things that we were, when we were going out to do sanitary surveys or source water assessments, understanding your water distribution. Again, what kind of factors are going on? What kind of maintenance is going on? Looking at surrounding land use practices. So do you have cattle that are watering in your irrigation source? Can you talk to your rancher next door and have him move his water source for those cattle upstream or uphill so that, you're reducing that risk? And really trying to identify those potential hazards within your watershed. All right, so what happens to those pathogens in the environment? We're talking a lot about die-off and potentially what can happen in the variabilities that we see. So when we think about pathogen decay in the environment, it really, again, is providing that retention time that we talk about a lot, allowing additional opportunities for die-off or attenuation of those microbial contaminants in the environment. So you might have a illegal discharge, and then that water is in that canal or that river or that lake or that stream for a certain amount of time. That time is going to allow things to happen to that bacteria or those viruses potentially. And what do those look like? So a lot of times, again, we think about survival of microorganisms in the environment, and we think about what are the different factors that play a role in their degradation or die-off. So things like temperature, we talk about UV light a lot, right? So UV and radiation, those oxygen requirements, and what nutrient requirements or what nutrients do those bacteria and other pathogens need to kind of hang on for a little bit longer. A big thing that we'd like to talk about specifically in surface water systems is the ability of those microbes to be transported, right? So water is a mechanism that transports those pathogens from one location to another, and so you think about that as a vector. We talked about rainfall and runoff and the impact that that could potentially play in, again, transferring those pathogens to that water system. But really, when we look at data historically, we do see reductions in bacteria, viruses, and some folks have mentioned the protozoa, the cryptosporidium and the Giardia, potentially over time. What's important to know, though, is that they all have different die-off rates, right? And I'll show an example of what one of those looks like. But I just wanted to also put this up. So we talk about the ag water rule and the 0.5 log die-off, and this is just an example, just again to kind of wrap your heads around it. And I'm not saying this is okay or not okay, but just to think about. So potentially day 0, you could have 10,000 colony forming units or CFU per 100 mils of water. By day 1, you're at 1,300. By day 2, you're at 1,000. Day 3, you're at 317. And day 4, you're at 100. So you're looking at that 4-day cap, and you're looking at potentially meeting the rule at day 3 or day 4. But as an industry, are you okay with knowing that potentially there could be a water source with 10,000 E. coli per 100 mils used and still meeting the rule? I'm not going to say whether I agree with that or not. I'm just going to say. I'll move on. All right. So pathogen die-off, what does that look like? How does that vary? Is 0.5 log per day an acceptable value? So in general, right, we think that pathogen cell numbers decline over time. So that's just a general term. And then they might die off more rapidly, they might die off more slowly. And what we might see is that decreasing concentrations with increasing temperatures in irrigation water. And so there's documentation in the literature that shows that to us. However, there's also literature that says E. coli 0157 can survive up to 8 weeks at 25 degrees C in the environment. So we know that bacteria is able to survive. We know that we're able to detect it at extended periods of time. It's just how fast is that rate? How quickly is it declining? And how quickly are we getting to an acceptable risk level? And what we've also seen in the literature is that Salmonella, a specific pathogen, can survive longer periods of time than E. coli. So again, back to what are we monitoring for? Does E. coli make sense when we're really concerned with some of these other specific pathogens? And again, I just did a real quick lip search. I pulled one paper that was looking at log reduction and die-off. So what we're starting to see in response to the FDA regulations about 0.5 log die-off per day, but also the allowance of alternative data to support that, we heard someone yesterday talk about at least 2 CPS, Center for Produce Safety projects that are focused on die-off. There's a ton out there, but it's all very site-specific. Right? And that matters. The die-off that I'm going to see in Arizona is different than the die-off I'm going to see in a wet, colder, rainier climate, right? The UV plays a huge role. The transmissibility in water plays another important role. The temperature plays another important role. And so again, thinking about what kind of data is being generated, and just looking at this, these graphs are time here on the bottom, and this is looking at fecal coliform concentrations on the left on this one, and this is looking at enterococci, and they're creating die-off curves related to exposed sunlight radiation intensity. And again, thinking about that's 2 factors that we're evaluating, but there's more than just those 2 factors that play a role in die-off. All right. So back to the risk assessment. So some of the work that we did previously was taking literature related to die-off that was available at the time and applying it to a risk assessment model. So applying it to that stepwise model that we talked about and seeing how that played out for the irrigation of leafy greens. And so we, from the literature, know the fraction of E. coli that's transferred to lettuce, and specifically we're looking at leaf lettuce. When you're irrigating with water that's been inoculated with E. coli. We know the adjusted per capita consumption of lettuce in the US, and we made assumptions that consumption of lettuce occurs 1 day after irrigation. That might be true, that might be false. These are the assumptions that we used. And when we look at that, so on this graph we have dose of the organism on the bottom, and we heard earlier about the US EPA level and the WHO level. So US EPA right here, that's 126. WHO is 10,000 dose. And if we look at the historical data and then we look at the different types of irrigation, we can calculate that probability of risk of infection here on the left-hand side. And what that looks like is dependent upon the irrigation practice, there are different risks associated. And this is all looking at assuming irrigation water has 126 E. coli per 100 mLs, right? So for a subsurface irrigation, 9 in 100 or 100 million. Furrow is 1.1 in 100,000. Sprinkler is 1.1 in 1,000. So again, going back to what's an acceptable risk? We can calculate that, but we need as an industry to decide what is acceptable. And then you back out what that number might look like. So when die-off isn't enough, when you're not able to meet the potential for die-off, what do? So a lot of talk has been given, again, about water treatment. And so one of the things you want to talk about is that we're having a bit of anxiety about monitoring and the costs of monitoring. That pales in comparison to the cost that would be associated with treating your water source to meet the rule. That's not even a fraction of that, right? It's ridiculous, the orders of magnitude differences you would see in having to treat your water sources continually over time to meet that rule versus what it would be to do the monitoring to prove that you are not meeting it. So that's part of the discussion I'm not sure we've talked about. So why would a grower want to treat their water? So obviously, if you're exceeding those standards by FSMA, you might have buyer requirements that might be a little bit more stringent than FSMA or FDA. You potentially have had past positive hits for pathogens, if that's E. coli 157, Salmonella, Listeria. Or you, and we've seen this, you have marketing or branding protection, right? Or you want to potentially say, I'm one up on the competition. Again, I'm not saying that that's right or wrong. I'm just saying things are the things that we've seen in industry and the way that people are using water treatment to market their product. So commonly used water treatment technologies. So we kind of break them up into 3 different areas. There's physical removal, so that might be some sort of filtration. UV light falls into the physical category, or heat sterilization. And so again, depending upon what you're doing, what kind of water source, there's different applications for these. Biological is another commonly used, and that's often looking at either constructed wetlands to kind of slow down the movement and the retention of some of these either chemicals or bacterial pathogens, viral pathogens as well. Or we've also seen kind of sand filtration. So you build up a biofilm on those sand particles, and they have the ability to bind up other contaminants. But largely the ones that we're considering and are often talked about related to the ag water rule and meeting the water quality requirements fall into the chemical category. And so I'll just let you guys look at those. So there's various combinations of these. There's combinations of these together, but generally these are the categories that we often see related to water treatment. So some of the important considerations for effectiveness. So again, all of those things that I talked about earlier that impact the ability of E. coli to survive and thrive also impact the ability of you to adequately treat that water and that disinfectant or that sanitizer to be effective. So things like turbidity, organic matter, that microbial loading. We talked about the volume of water. Are we talking millions of gallons? Are you talking acre feet? Are you blending a water source? That's a huge component to if you're going to be able to treat this effectively. We talked about the treatment technologies largely driven by energy requirements. Is this something that you're going to have to now pipe some energy source out into the field? Are you going to have a generator on site? How often is that running? What is the fuel cost associated with that? So again, things to think about. One thing I'll talk about in the next couple of slides is on-site monitoring and dosing. So none of these systems are set it and forget it and walk away. You might have a company that's trying to market that to you, but I'm going to tell you right now, nothing works like you think it's going to work when it's challenged. You have a slug of turbidity coming through. You have some disturbance upstream that's overloading your system. You're going to need to have someone who's there, or at least remotely, monitoring information that's coming out of some of these treatment systems to have the assurances that it's actually working like you think it's working. And so that's an important consideration. And scale. So is it mobile? Can I move it around? Does it need to be stationary and built into one place? Do I need to pour a cement pad and have it sit there? Or is it something that's on a trailer and that's moved around? What risks are associated with that? Not just pathogenic risks, but chemical risks, right? Spills, contamination, different things like that. So you guys will all have copies of the slides so you guys can read through this chart, but I basically just wanted to highlight some of the things that are factors in the ability of you to be able to adequately treat your water. So organic matter, contact time, pH, temperature, and turbidity. And I'll just focus on the solutions to that. So these are all potential issues or problems, but oftentimes if you have high organic matter, you're gonna have to pre-filter your water so that your disinfectant's gonna work properly. Again, something that is not often thought about. Contact time, so nothing is immediate. You have to have the right amount of time of that disinfectant or sanitizer to come into contact with that water product or the bacteria or the E. coli, whatever you're trying to disinfect, to allow it to work, to allow that bacteria to die because of that. Many disinfectants are dependent upon these guys right here, pH and temperature. So you've got to be monitoring those. So again, you're not just monitoring the dose of that, but you're monitoring what's the pH look like, what's the temperature look like. And finally, again, that organic matter and turbidity, talking about filtering that water. So what are some other things related to successful implementation of water treatment technologies? So again, will it work? And how do you identify ahead of time if it's going to work? pathogen loading, that contact time, those dosing requirements. I mentioned about capital equipment costs as well as operation costs, but again, some of those other things that are not often talked about. What is the worker safety components related to a treatment technology? And what's the ease of use? Are you gonna have to hire in a new somebody to do another job for you? Can you afford that? Does it make sense? How do we fit that into a cost-benefit analysis? And I just wanted to put over here is just kind of a generalized ranking about related to costs and how some treatment technologies like ozone are going to be more costly than things like sodium hypochlorite or peracetic acid, something like that. All right. So I wanted to walk through kind of my last couple slides of examples for chemical disinfectants. So again, something it's not often talked about or discussed, at least in the ag world, it is in the water world, is that disinfectants and sanitizers don't kill pathogens instantaneously, right? It's not like we're gonna add this in, they're gonna die, and I'm gonna be ready to go. It often depends on different factors. So what's the pathogen you're trying to reduce? What's that chemical concentration or that sanitizer concentration that you're working with? What's that contact time? We talked about that before. The temperature and the pH of the water. And so how do we know if we're doing this correctly, right? So I'm not a water treatment operator, but you have to become one. And so what are the things that you have to learn? So if we're going to impose this on growers, or growers are going to have to implement these, what types of educational programs and resources and tools are currently not available that are needed? Okay, so we talked about CT values and CT tables, and this is an ode to the EPA. And so this is just an example that was adapted from the EPA. This is a disinfection table for EPA on CT values, so contact time and concentration time, looking at Giardia and looking at free chlorine. So again, I'm just using this as an example. Here's the chlorine concentration. So we've got temperature and pH over here, and you've got the chlorine concentration over here, and this is your contact time. So this is the amount of time that you would need to get a 3-log inactivation of Giardia at that temperature. Again, there are resources available, but again, it's more than just a plug-and-play science. And so a couple of rules of thumb related to water treatments is about the monitoring and is about how you're testing your system and making sure that it's working properly or appropriately. So in general, chemical disinfectants are often more effective with decreasing pH, with increasing temperature. And so again, having to monitor these systems over time, depending upon your season. You might be more able to meet your contact times in the summer than in winter because you have higher temperatures, and that plays a role. So again, you're constantly kind of evaluating and monitoring these systems. And then I stole this from one of the companies that we work with on how else are you verifying proper use of that chemical. And so you might have these little test strips or dilution tubes, things like that. But again, you have to have somebody who's sitting there actually monitoring these types of systems. So what grower tools are currently available, and potentially what can we develop or what are needed as we move forward? So obviously we've talked about risk assessments and how that can help, and I'd really like to see the next part of the conversation really driven around that. We've mentioned a couple times on-farm readiness reviews, and so again, that's one opportunity that trained individuals can talk to growers about the potential that they're doing for their water sources and water treatment technologies and what may or may not be useful resources for them. Obviously, cooperative extension, I'm going to plug what I do, right? I'm a cooperative extension specialist, and so often we've heard, cooperative extension can help you, but we need the funding to be able to help you. So again, a shameless plug for more money for our program. Industry organizations, obviously water treatment manufacturers are really big, but I want you to be able to be prepared to question and to poke and to prod and to say, this is not the silver bullet that's going to solve all my problems. If you're considering a water treatment technology, there's many types of questions that need to be asked related to that. And one thing that I wanted to point out, several of us in the room, Manon and Dr. Gerba, and a lot of the remote sessions are part of a USDA NIFA project called Conserve. So here's the website, conservewaterforfood.org. And I implore you all to look at that as grower resources related to water, water quality, water options, water treatments for growers moving forward in the face of climate change. All right. Also have to do a shameless plug for our Ag Water app. So who here in the room has heard of, seen, or played with our Ag Water app? Yes, almost all the room for the remote people. Raise your hands too, the remote folks. Everybody take a tally. All right, so this was related to the work that was initiated by Linda Harris out of the Western Center for Food Safety. Again, thinking about FSMA, thinking about how growers are going to meet new FSMA requirements. How are we going to do calculations? How are we going to understand the die-off and the complex math? So there's many different resources. There's the web page that you can go to. You can download the app. There's the online calculator that you can kind of download, and then also the download Excel spreadsheet out of the Western Center for Food Safety. So again, lots of options to be able to provide resources that you could start playing with. And so one of the things that we've talked about in a lot of the PSA trainings, if you are starting to collect water samples, plug them in and start playing with it and just kind of see where you fall, right? Like if you're going to start collecting data, what does it mean and how can you start to wrap your head around if you're going to be able to meet that potential rule or not? Additionally, one last kind of slide related to additional resources. So actually, another raise of hands. Who here has seen Donna's amazing Excel spreadsheet and an online video related to sanitizers? A little less people. So here's the website. On the Produce Safety Alliance, and basically what she has done and what they have done is kind of start to pull together a common list of sanitizers that are currently used and to provide context and information about, is this allowable for irrigation water, is this a post-harvest sanitizer, and some of the things to consider. The EPA label is there. She's got a great little video that kind of walks you through that. And so again, another resource for growers to be able to better understand the options that are available to them. And with that, I will end. All right, thanks. Yeah.
We get one question.
One question. Yes, sir.
I have a question and maybe also a comment about the microbial die-off. I appreciate the clarification on that. When we talk to growers and we say they configure a microbial die-off of half a log a day for maximum 4 days, it's over their head and it's gone. And then they come back with things like, if my fruit, edible part of my plant starts at flowering, do I have to quit irrigating then when they've already got a tool? You test your water, you figure your microbial die-off, and you quit irrigating at that time. The question is, do we have a document available that says if my water profile is this, I use a 4-day pre-harvest interval. If my profile is this, do I use 3-day, et cetera? That would be very helpful.
Great, yeah, so it's part of the app and it's part of the online tool, but there's been talk about creating a standalone chart or a standalone table that could be used as a supplemental resource.
Longhand version that you can do the calculations yourself, but I think what you're presenting is a great idea to have a chart that says, you know, if your water is this, you know, this is the number of days, so you don't have to walk through that very long calculation process by hand.
Yeah. Oh, Channah, you didn't get your gift. One more round of applause. That was beautiful. Good job.